Tá joia, então tá. Porque aí...
Você tem o canal para conferir, Hilário?
Mas deve estar. Eu tô olhando aqui, mas eu posso entrar no canal para ver, né? Mas acho que não tem problema. Se está dizendo aí que está bem...
Olha, ele diz que sim, ele inclusive está me mostrando o canal, seminário de probabilidade.
COLMEA, qualquer coisa lá. Isso. Vou ver aqui, mas acho que deve estar.
Perfeito. Bom, vou desligar minha câmera.
Então, estamos prontos. Okay, so this seminar is slightly different. We are making an effort to join a few of the seminars we have that include INPA in the organization. And today we're having our usual seminar with joint with COLMEA. So that also implies another difference, that we're going to have another seminar that is COLMEA only after this one. So everyone who wants to stay for longer is very welcome. And today we have Marcelo Hilário from the Federal University here at Minas Gerais, who's going to talk about percolation with directional disorder. So please, Marcelo.
Thank you, Augusto. It's a pleasure to speak in this joint seminar, COLMEA and the usual seminar on Wednesdays. And so thank you, and Eulalia, Claudio, Pablo for the invitation. And my title, I think I gave a title with the cubic lattice standing there, but maybe I will not talk too much about the cubic lattice, but more about the square lattice. Well, we'll see. So since this is joint with this COLMEA seminar, to stay in the safe side, I will start like very basically recalling what percolation is. By the way, Augusto, how much time do I have? Well, okay. I'm assuming I have like 50 minutes or something like
50 minutes,
that. So,
yes, Marcelo, you have 50. Augusto, you can't hear. You can't, you're mute.
So, okay, so let me start.
Sorry, I was mute.
So
Yeah,
as I
50.
was saying, let me start in the safe side. So recalling what's a percolation process. So giving a lattice, let's say the square lattice, I will assign random variable 1 or 0 to each edge of this lattice. And whenever you see a 1, I will think that the edge is open and a 0 closed or present or removed. And then this gives rise to a random subset of this lattice. And we can see a picture here. And we are interested in studying connectivity properties of this random subset, like size of clusters and whether or not one given point is connected to the boundary of the boxes or quantities similar to those. Okay, so the simplest thing that you can do is to assign the states of the edges independently with the same probability. So let's say P. And here I prepared three pictures with different values of P. And you see on the left, you have low connectivity. The thing is essentially all disconnected. While in the right, you have something much more compact. So you see you have a robust structure. So you have crossings from one side to the other, from bottom to down, from bottom to up. And in the middle, you have something in between that in principle may look a little bit like the one in the right. But if you check carefully, you're going to see that it's very fragile in the sense that if you if you just switch the state of some few edges or maybe one edge, you're going to change the fact, for instance, that there is a crossing from one side to the other. Okay, so this three kinds of behavior divides the phase state in three different phases. The left one very disconnected, and you see here I have painted the largest components in the boxes here. So here you see all components are very small if compared to the size of the box. On the right, you have a giant component that takes almost everything. And in between, you have this thing that wants to become a giant component, but it's still a little bit, it doesn't take too much of the volume of the box. So some quantities that we would like to study is, for instance, the probability that the origin belongs to this giant component. And if you increase this value of P, the parameter, then one time you want to keep track of the first time when this quantity starts to be positive. So this is the critical point. Should be this value of P that gives this picture in the middle. And you also want to keep track of other quantities, like for instance, the probability that the origin connects up to distance n is what's in the right side here. And it's well known that you have three different phases: the subcritical phase, the supercritical phase, and the critical phase just in the middle, separating these two other phases. And here you have an infinite cluster that is unique. And on the left, in the subcritical phase, you only have finite components. And here I want just to call your attention that in the subcritical phase, the probability that a given point in the bulk is connected up to the boundary of the box decays exponentially fast in the size of the box. And same thing here, if you want to connect to distance n, but not touch the giant component, then this probability also decays very fast. In the middle, you have this signature of the phase transition that it's the power law decay. It's just expected to be found in the critical phase and not in the subcritical and the supercritical phase. All right, so my goal here is to talk about some more exotic kind of percolation, where we introduce either a strong correlation between the edges or the sides of the lattice, or we just let P change, the parameter change from column to column or from plane to plane in this lattice. Or maybe we decide to pass to a dilute lattice. So we select some columns at random and just drill through these columns and get a random lattice, which behaves like a random environment. And on top of that, then you can run your percolation process. And I'll try to show towards the end some techniques that we use to control these processes. So we have to control both the environment and the percolation on top of this environment. And the technique that we're going to use is renormalization. All right, so to start with, let me start with a model that I really enjoy. And I've been working with this one since 10 years ago. And so imagine that you have this cube made of wood, and you decide to drill through each face to the opposite side with some probability that can depend on the direction, right? So you remove straight lines instead of single bits in the in your media there. And this was first introduced long ago by Cantor, and then studied with co-authors, including Augusto and Nuno, who are in the audience in this paper here. And so what we know about this model here. So first of all, the math definition, I just mentioned, you remove parallel lines in the infinite lattice with probability 1 minus p, depending on the direction. Okay, so I'll keep 1 pi for each one of the directions. And the goal is to study these connectivity properties of what remains. So not the set of lines, but what's not touched by these removed lines. So a theorem that we proved with Vladas a while ago, and was published only in 2019, is that if one of the parameters is subcritical, but for the usual site percolation process, then already the probability that the one given site connects to infinity is 0. And so what's happening here, if you drill too much in one direction, then you are already doomed, because you're going to separate your original lattice into cigar-shaped, like cylinder-shaped regions. Then you're basically one-dimensional, and then you're going to get killed by the drilling coming through the other directions. And on the other side, if you take all the parameters large enough, then you percolate. So no surprise here, it's a usual phase transition, right? And here I have a picture of a simulation in the paper with Nuno and Augusto and others. Here, the simulation is for d equals to 3, and all parameters, so you're drilling in all directions with the same intensity. And then we found a phase transition around this value here, which is strictly bigger than the critical point for site percolation in Z2, which should be something like 0.59. So here you see this pi is the probability of crossing from bottom to top in a box. And you have something happening around this value here. The probability goes very quickly from 0 to 1 around here as you increase the side of the box. All right. So this is just the phase transition for this model. But what I think is interesting is related to the sharpness of the phase transition. Because if you recall, for Bernoulli percolation, you have exponential decay on both sides, and something different can only happen in exactly on the critical point. And here the picture is much more complicated, because we have the following. If you drill too much in a few directions, let's say 2 directions, then you have exponential decay already. On the other side, if all the parameters are sufficiently large, then let's say all but 1, then the probability that you connect up to distance n, but not to the giant component, cannot decay exponentially fast. It can decay at most as a power law. So it means that if you take, like now, P1, who doesn't appear here, very small, then you already disconnect everything. Then this part here is not necessary inside the probability. And you see, you are within the disconnected phase, and you don't have exponential decay. So the picture is a bit more complicated in this case. So you see, you have some kind of extended phase here. Let's say this picture is for d equal 3, and all parameters equal to p. So I'm drilling with same intensity in the 3 directions. And what we have here is that we have a phase that it's very disconnected. You have this exponential decay. Then you have a phase where you have a giant connected component. And in this region here, you have at least a lower bound that it's a power law. And it's an open problem from the math point of view to prove that this gap really exists. So I mean that this quantity P star, the critical point, is strictly bigger than PC of Z2 in dimension 3. And but it's clear from the simulations, as I showed in the last slide, that this gap really exists. So you have this intermediate phase, and this is what I consider to be very nice in this model. And I think I included this model mostly because it really illustrates that when you're dealing with these strong correlations along lines, then the nature of the phase transition can change substantially. All right, so let me now go back to the square lattice. And another way that you can introduce lower dimensional disorder is by selecting some columns, let's say this set of columns that I will call B right now. So they are just marked in different color here. And I will decide whether or not edge is open depending on the location of this edge. So if it lies on one of these selected columns, then I open with probability Q. Otherwise, if it lies in a blue column here or it's a horizontal one, then I open with probability P. So now I have these two parameters. So this model has these inhomogeneities. And now, once again, if you quench your disorder, so you have your condition on these lines, then the state of edges are going to be independent, but inhomogeneous. Now, if you average on the disorder, then you have infinite range dependencies that just spread along this vertical direction. So there are several well-known cases, and two of them degenerate. Let's say that I only choose a single column to change the value of the parameter. And in this single column, I will, let's say that I start at the critical phase, and then I give a boost here. I just increase a little bit the parameter in this one single line. And it's not enough for create an infinite cluster. So regardless of how much you try, as long as you don't hit one, of course, you're not going to be able to create an infinite component. This is a result from Zhang in the 90s. On the other extreme, you can think, okay, let me just enhance the parameter on every line, every vertical line. Now it's a line that it's painted, like in the previous slide. And then something interesting happens. If you increase this parameter by a bit in the vertical lines, you can decrease outside in the horizontal lines. And if you increase faster than you decrease, then this is already enough for you to create an infinite cluster. So this result is due to Kasten in the 80s. And much more interesting is to think of what happens in between. And that is this technique due to Eisenman and Grimmett that allows us to study this type of problems when you have these columns, let's say periodically spaced in the lattice. And what this formula here says is that, suppose that if you increase the, you can increase the parameters in this set of lines B and decrease in the outside, not too fast, then you still percolate. So it's similar to the previous one, but now you don't have, maybe you have to decrease much slower outside the vertical lines on B, because you have to account that this enhancement is being done in maybe very sparse set of columns. So, so this says that if you increase, again, from the critical point, if you give a boost in these lines, you make it better for percolation in these lines, then you can even decrease outside with a certain delta that is going to depend on epsilon and on the set B, and you are going to have percolation. All right, so of course, when we think of disorder, we may pick this set of lines at random. So this is what is more interesting, and the problem with this technique of Eisenman agreement is that it usually breaks down when you choose this set B with lines that can be very, very, very far away. So if you're just tossing coins in order to decide whether or not a column is going to be enhanced, then maybe you're going to find very large regions where you don't enhance anything. And this technique, the way it is stated in their paper, is completely breaks down in this case. So we consider this case when the spacing between these columns are given by a geometric random variable. And what we got is that the same result, okay? Now, regardless of the density of the lines and of the amount that you enhance in these lines in B, you can still decrease a little bit outside and have percolation. So in words, even when good is just slightly good, it's just C plus epsilon, and it's very, very rare. So if this rho is very small, if you do not do too much damage here, you should not decrease too much the parameter outside, then percolation will still take place. And there are some other results in the same direction, and I will not be fair to lots of people who have worked on that same kind of problems. But I just wanted to mention two works in oriented percolation or in the contact process in the same spirit. So these are the works of Bramson, Duhet, and Schoeman, and Kesten, Sidoravicius, and Varis. And what I think is interesting here is that, so the setting is different in all of these papers, but what's more interesting is that the order that you change the parameters give different kind of results. And so in this paper, Bramson, Duhet, and Schoeman, they consider the contact process, and they have this good lines in the direction of time. So it's oriented in the direction of good lines. And let us assume that the other lines are very, very bad. And these good lines are rare. If you make these good lines sufficiently good enough, then the contact process still survives. On the other hand, Kesten, Sidoravicius, and Varis, they studied oriented percolation, which is similar to contact process, discrete version, but now with the bad lines transversal to the direction of time. So it's a much more complicated problem in this sense. But the qualitative picture here is that if bad lines, even if bad lines are very bad, if good lines are just slightly good, and bad lines are very, very rare, then these bad lines are not going to be able to disrupt percolation, even though they are perpendicular to the time direction. And our work from the previous slide, as I mentioned, the order that we pick the parameters is different. So if good lines are just slightly good and very rare, then if bad lines are not too bad, they cannot disrupt percolation. So these are the three kind of problems that you can try to study in this setting of good lines and the bad lines transversal to the time or parallel to time or even non-oriented in our case. All right. So a very similar kind of problem is when we now are back to the square lattice and we try to dilute this lattice. So if I just drill like in the cube, in the works in line, in this drilling percolation, and I drill through the sides and then try to do side percolation, then it's not going to be good because I will just disconnect the lattice. So the nicest thing to do here is to just delete edges at random in some locations in your lattice. But you see, even if I delete all this column here, I can still connect just going around. So I will pick one variable, let's say integer valued, and prepare lots of copies of this random variable independently. And I will remove I will just keep the ones that are spaced by these random variables here and remove vertical edges in between. So this gives rise to one-dimensional random environment here of columns, which I can mark with this x0, x1, and so on. And outside this, I will just delete the columns. So in what remains from my lattice, I will declare each side open or closed with probability P. And you see, now you can just replace one horizontal edge like this one by a longer edge whose probability of being open is P squared, because you pay P for opening this one and P for opening this one. Then to connect from this side to this one, you have P squared. And this square comes from the fact that this random variable here assumes the value 2. So what I really want to do is to pass to the continuum. Let's say now every random variable is allowed, positive random variable is allowed regardless whether or not it's integer valued. And I will open horizontal edges with the probability P to the side. So I'll just repeat this in the continuum. All right, so edges are just open. Horizontal edges are opened according to the value that this psi random variable assumes there. Is it clear, the model? In case anyone has some doubt, I'm available I can read the chat, so you can just post. So I think it's clear the setting now, right? So the question is, like, does phase transition always occur in the setting? And if so, how does it depend on the law of these random variables that you are using for stretching the model? So this has been considered in in other works. And in this work of Jonasson, Mossel, and Paris, they consider stretching in ZD, so D dimensions, and in all directions, not only in one direction like here. And also in the work of Hoffman in 2005, they consider two dimensions only. And in all these works here, the psi random variable have to be geometric, all right? So we want to let go from this geometric setting where the spacing is geometric, and really study how the amount of stretching or the moments of this random variable interfere in the presence or not of percolation, right? So our theorem, together with Augusto, Remy Sanchez, and Marcos Vinicius Sá, is the following one. It says that if the tail of this stretching random variable decays sufficiently fast, so meaning that this moment of order 1 plus epsilon is finite, then usual phase transition occurs in some sense. So if you have P larger than a critical value, then you have an infinite cluster, almost sure. And this for all realizations of your disorder, almost all. Now, if you take P smaller than this critical point, then probability that the origin connects to infinity is 0. So you really have a classical phase transition in the sense that you have a disconnected phase and a connected phase. But sharpness, exponential decay shouldn't take place in all the subcritical phase. I will not come to this detail. What's interesting is that now if you stretch too much, then you completely destroy the phase transition, in the sense that it doesn't matter how large you make P in the interval 0, 1, you are certain that percolation is not going to take place. So this can be improved to first moment, but so here, if first moment is infinite, then we know how to do it, and they'll show that percolation doesn't occur. But on top here, we don't have any substantial improvement from this condition, meaning that maybe with some effort we can put something better than this, but we cannot get to first moment. So an open problem here, which I think it's interesting, is to determine whether or not this change of behavior takes place exactly when first moment is finite or not. Okay, so the proof is based on a separate control of the environment. So first you try to control the environment, and then on top of the environment, you try to control percolation, and this is done usually using some kind of renormalization techniques. And in the remainder of the talk, I will try to give some hints on how to prove this result. But what I wanted to mention is that all of the results that I talked previously, they also, their proofs also go in the same direction, in the sense that you come with a renormalization argument and try to control first environment, and then once you have the environment controlled, you try to control your calculation on the top of the environment, right? So I wanted to pick one of these problems to show the techniques that we used, and I've chosen this one. That is the last one that we worked on this topic. And let me start with the control of the environment. And usually for controlling the environment, we need something that we call a decoupling. And let's say that I will be in the setting that this size here, this side here, they all have good moments. So I really apologize for the noise. So I think it's good, right? Can I continue? So yeah, I'm sorry. Today it's really.
It's not very audible.
Okay, good. So so here I have this random variable psi, and let me assume that they are integer valued and they have good moments, meaning that when I take the 1 plus epsilon power and take expectation, this is finite. So have good moments, right? So maybe introducing some well-chosen delay here in the beginning, I can pass to a version that it's translation invariant or shift invariant in some sense. And this is good for what I will do later on. And I will assume lots of good properties of this random variable so that I can think of it as a renewal process in the integers, like here. So let's say that I mark a 1 every time I have a renewal here. So these are the positions where I will have a column in my original setting, right? So you remember in the original setting, the columns are separated by this stretching that's given by C. So if I have one column here, then I have another column here. So a sequence of zeros and ones like this just encodes all the randomness in the environment. So it's really one-dimensional disorder in this sense. And here below, I just made a drawing of the renewal chain. So here you have the time until the next renewal. So here I will renew in the next site. So I have a 0. Sorry, maybe. Yeah, here I have a renewal, so I have a 0 here. Then a 1 because I am 1 unit away from the next renewal. Now here 4 because my next renewal is here, 4 units away, and so on. So this is classical Markov renewal chain, right? And if you assume all these good moment conditions on this variable psi, then what's nice is that we have this good control on the correlation or the covariance on what happens in faraway regions on your environment. So if you take a certain event that's measurable on the configuration of the environment in a given place, and then you have a gap, say of size n, and another event that it's measurable with respect to the environment here, then they are essentially independent if this value of n is large. And this epsilon here is the same epsilon that appears in the statement of the theorem in the moment condition. So if you have good moment condition, let's say if epsilon is large enough, then this decay is even better for you. So, so this is key property of our techniques. So whenever you have this decoupling, then it's good for you to control the environment. So how we do it? So we start by picking a sequence of scales, and you should think of this as numbers that are growing very, very fast. And what I do is that I will tile the Z axis here with intervals that are given by this scale lengths, right? So I have here scale k+1, and it's tiled by blocks of the previous scale, which are tiled by blocks of the previous scale, and so on until you get to single points. And once we have this construction, these multi-scale blocks, I will define what I mean by a block in each scale being good or not. And this is a recursive definition. So what I do in the first scale, this is scale 0, I declare one box or one interval being good if I have a 1 inside, or in the original interpretation, if there is a column that is gonna pass here. So a vertical column of the lattice passing here and here, and bad otherwise. All right, so you have good, 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 good. And see, if I choose this L0 very large, then the probability of being good I can make as high as I want. So now I will move recursively to higher scales, and I will do so in some way that I create a kind of healing process. Even if something is bad in a higher scale, in a small scale, then maybe looking in higher scales, it can become good, right? So what we do is the following. So in a higher scale, like let's say k+1, we inspect all the blocks inside, and we say that it's good if there is no two consecutive two blocks that are bad inside that are not
intervalos bons e intervalos ruins. Aí você usa tipo um teorema tipo.
Okay, I think someone asked the question. Did anyone? Okay, I thought I heard the question, but no, everything fine. Okay. So so here, this block here at scale k+1, this is bad because it has two bad blocks from the previous scale that are not consecutive. But this one is good because even though there are two bad blocks in the previous scale, they are not, they are consecutive ones. And here you have three, meaning that this one and the last one, they are not consecutive. So this is also labeled bad because of that. So you see, even if something has something bad in one scale, it can become good in the previous one. Sorry, in the next one. So you have this kind of procedure here. So what's the main idea then? Is that now if you define pk, the probability that one block is bad, so it doesn't have much columns passing there, you have to control this quantity. And what you do is you want to show that this quantity is small. So you don't want to see bad blocks here. You want to see good blocks. So what you do is you take this block at scale k+1, And if it's bad, it's because you see at least 2 bad blocks inside. So this is the amount of ways that you can pick 2 bad blocks from scale k within scale k plus 1. So the square, it's because of the pair of boxes, and this is the amount of ways that you can pick a single bad block inside. And now you have to have 1 bad block, another bad block. This gives pk to the square if they were independent, but they are not. You have this decoupling. They are almost independent if k is large and epsilon is something positive. Right. So what you do now is that you try an induction procedure. You just try to come up with a bound here. Let's say that pk is smaller than lk to the minus alpha. You plug here and see if you get the same thing happening in the other, in the next scale, right? So here it's gonna work as soon as this alpha is of order epsilon over 2, because you have a 2 here and an epsilon here. And then this is just simple calculation. You just plug it there and see that you have this induction going on from, so you propagate from scale k to k plus 1. But in order to have this pk small in all scales, what you need to do is to have then the first scale satisfying this bound here. So what you do is you take L0 large enough. So already in the first scale, you have this bound. Then by this inequality, you're going to have for all the next scales. Okay, so this gives the control of the environment, and meaning that for every k, the probability of having a bad block at scale k decays fast. And why I call it fast, it's because this lk grows very fast. Then even if this alpha is something tiny, then this is decaying fast enough. So by Borel-Cantelli, if I inspect some large region of my environment, I will just see good stuff. All right, so I'll rely on that in the control of percolation. So if I can just take like 5 more minutes, I will now assume that I will have only good environment, and on top of good environment, I will show how to control the percolation. So here in this specific model, I have to come up with some height scales that are different from space scales. So what you should imagine here is that the height is much, much, much bigger than the width of these blocks in the lattice that I will look. So I'm back to the 2-dimensional lattice to study percolation. And the heights are going to be stretched exponential, roughly speaking, if compared to the horizontal lengths of the blocks. So I have some pictures like this, and it's somehow misleading because really this should be much, much bigger than the horizontal scale here. And what I do is that I define horizontal and vertical crossings in these blocks here. And I want to bound this quantity here is that the probability that no crossing occur, even though the environment is good. So I will come up with some kind of induction procedure as well. So I assume that the probability that no crossings occur in scale k have very small probability, and try to propagate this bound to the next scale. And how I do this, first for horizontal crossings, since this height is much bigger than the width here, I will have many attempts to cross. So I take one of this and zoom down here, and I'll try to put together crossings of the previous scale, and they happen with overwhelmingly probability. So when the environment is good, but if the environment is good, I still allow for bad regions like this, or maybe two consecutive ones. And when I get to these bad regions, I'll have to cross. And the dumbest thing that you can do is try to cross straight here. So what price you pay? You pay exponential, but of minus the previous scale. So it should be exponential of minus LK here, which is not bad if compared to this, because you are choosing the scales to be LK plus 1 equal to LK to a power. So anyway, you pay this price and continue to put together these crossings. And then you have some probability of crossing here, which is good enough. And then when you take account the many attempts that you have in this disjoint strips, then you can obtain this bound in the next scale. So this is done for horizontal crossings like this. Now for vertical crossings, you try to do something very similar. So you try to put together crossings like this and try to find a crossing from bottom to top. And again, if the probability of finding a crossing like this is large enough, then you almost don't pay anything for putting together these guys. And even though they are a little bit dependent, they depend on the neighbors, you can show that the probability of crossing from bottom to top in the next scale is still high. So this is the complementary set, right? So the complementary set is small. So not having the crossing have very small probability. Okay, so this controls the crossing probability when you have good environment. And now just to finish the proof that percolation takes place when P is large, what we do is, so if K is large enough, then we only see good blocks because we have controlled the environment and showed that it behaves like this. Now, if you take P large enough and the environment is good, then these crossings are very likely to occur in every scale. Then you put together crossings of the first scale until you hit the next one. And then you put together blocks of crossings of this next one, and so on, and you build your infinite cluster like this. So you just need to start with one scale, then move to the other one, and these guys are going to connect to each other. So I think I'm running over time. So this was the proof that percolation occurs when environment has good moment conditions. I will not show the other part of the theorem, that when you stretch a lot, then you don't have percolation. And I think I will stop here. Thank you.
Thank you, Marcelo. So are there any questions, Marcelo? So just crossed my mind especially because Nuno is here and brings me memories of the time we worked closer with physicists. Besides the obvious models that we know, are physicists looking into this type of inhomogeneities and trying to investigate this intermediate phase? Do you know any work in this direction?
So I think that the question is more to Nuno than to me.
Nuno pediu a palavra.
Please?
Sorry, can I ask something?
Of course.
Yeah. Well, regarding your question, I think it's always important to look to anisotropies in the system. And so people have been looking to that from different perspectives. But I have a different question. So regarding this problem that you described first, where you have a two-dimensional lattice, where you have a different probability for these vertical columns, for these specific columns that you distribute, one of the things you said is that this increase in probability along the vertical direction, what you call, I think it was epsilon, needs to be larger than delta. So the decrease in probability along the horizontal direction.
Yeah.
And so my question is that a minimum condition or a necessary one?
So yeah, this is just to this case where I enhance all vertical columns. Then it's if and only if. So it's if you go faster here, then you decrease here. So if you increase faster than you decrease, then it's good enough.
Mm-hmm.
But here I'm just relying on the fact that all of these columns should be painted, these vertical ones. So you really have one parameter for vertical edges and another one for horizontal ones.
But what if you look into a density of those columns? So later you describe a case
yes,
where you have a density row.
Yeah, so if I have a density row like this, then I don't have this fine control. I only know that for all intensity of enhancement, I will have maybe a very tiny window here to decrease outside and they still percolate.
Okay.
So here the argument is very perturbative in some sense that we have to choose all these boxes and run our multi-scale arguments. Then it's really perturbative here. So I can only show that there exists a delta that is small enough such that if I decrease here, I still keep percolating.
Okay, because what I had in mind is the following. If you have a certain density, what you are saying is that you have an infinite number of those columns. And so somehow you have a characteristic distance between the columns, right?
Yes.
So you no longer need that the connected path goes to infinity. He only needs to exist within a certain length scale that is the typical distance between the columns. So I was expecting that even for values of what you call delta above epsilon, provided that the characteristic length of the connected paths is larger than the distance between the columns, that you will have an infinite number of those connections between the columns when you take the infinite system, right? Does it make sense, or am I thinking wrongly at some point here in my line of thought?
Yes. Yeah, qualitatively, yes, it makes sense. So so if you look from far away here, so you should have these bands where everything is good, and in between these bands where everything is bad, right? And you try to like grow your cluster in the good bands, and if yeah, so now you're going to have exponential decay in between, right? But if you have a very high density of connections, so in these good bands, then you have hope that very often you're going to cross the bad regions. But the pain here is to really have this qualitative trade-off between what you gain in the good regions, in the good bands, and what you lose in the bad ones. And so I think that what you described from the physics point of view, it's I think completely clear, but somehow from the math point of view, for us, it's a bit difficult to take all these scales in account, to account for all these scales and really prove it in a non-perturbative way. So probably this can be done, but I don't know how to control it as finely as you want. Like really, you want to give a much better control than what I have here. But yeah, you should be right.
Okay, thank you very much, Mark.
It's very interesting question, by the way.
Okay, if not, let's thank Marcelo again.
Okay, thank you.
Thank you, Marcelo. Very nice talk. So, as I said, this is an experiment, so we are still learning. We had a slight mismatch in the time schedule because the length of the two seminars is different. So, in principle, Nuno's seminar shouldn't start in sequence. We should have a break, but I think the break predicted in the poster is a bit too large because Marcelo's talk was shorter because it was joint. So should we make a shorter break, perhaps? And if anyone wants to continue in the chat, we welcome to, we can socialize a bit. And anyone who wants to leave and join later or has a commitment cannot join. See you next time. So just before people who may not stay leave, I would like to say that we continue on next Wednesday with, I think next Wednesday is Perla, if I'm not mistaken, Perla Susi from Cambridge.
No, Thursday.
Oh,
It's
yeah.
Thursday.
Yeah, thank you. So next week we continue with Thursday from Washington, and then Perla the week after. So thanks everyone. I think we should probably interrupt the live streaming from IMPA and continue the one from UFRJ soon. I don't know how to.
You can continue even put together all together, as you prefer. We can stay with one video only afterwards.
Okay.
If the transmission doesn't stop, there is no problem.
Should we schedule a time for Nuno to start? So if people want to do something else.
What time was it planned?
Okay, I have to check. Just a second. It was 2:20 Brazilian time, so that would be in 15 minutes. Maybe we can.
It's up
a
to
bit
you. I
less.
think we can start earlier, I guess.
Yeah.
Anyway, it will stay the video afterwards for someone comes later.
Yeah.
I think we can. It would be better to start to make a short break. It's my opinion, no? Because to be waiting for too long, I think it's too much.
Yeah.
I
Now
would
it's
make a short
2:04,
break.
so we can wait maybe 6 minutes and start at 2:10.
Yeah, I think it's good.
And Nuno, are you in Lisbon now?
Yes, I'm in Lisbon now. Yeah.
Is this your office?
Yes, this is my office. Yes, at the faculty.
Nice.
So soon you will be visiting us, right?
Yes. Really looking forward to.
Very nice.
Is the office are the activities retaking place now? Like in
Sorry, come again?
presential activities?
Yes.
classes
So now it's more or less all going back to normality. So even the
Great.
previous semester was already everything in person, and now we are continuing like that. And the rules they are somehow releasing some of the rules now.
I see.
Mainly related with the use of masks. It's still mandatory to use masks everywhere, but soon it will no longer be mandatory to use it outside, for example, and things like that. So yeah, hopefully things are going back to normality.
Hopefully, yeah. Here it's also, we are also experimenting with in room classes, but from time to time someone has some symptom and we interrupt the class for 1 week.
Yeah, okay.
It's working, but not without.
So now that
interruptions.
we have most of the population is vaccinated, even with a booster. So what they are doing here is that even at schools, if someone gets a positive test, this doesn't imply that all the school goes back home as before. So you continue until the next person gets a positive test. Yeah.
Yeah, that's probably what we are converging to soon as well. We don't have a big percentage of the population vaccinated with third dose yet, but I would say at IMPA, among the students, we're very close to that.
I think we are already all fed up of using masks and all this.
That's true. But yeah, one thing that I think I'll keep is whenever I'm having some symptom, keep using masks.
I know,
right?
yes.
Something people did in Southeast Asia all the time, and we never really caught that habit. But it's a good one. We should adopt it.
Yes. No, I think it's a good thing to do. So maybe I will share my screen just to see if everything is working properly. Is that okay?
Sure.
Is this? Okay. Is it working?
Yeah.
Okay, nice. Since I cannot see the chat, if during the talk someone wants to ask something, just let me know.
Yeah, I will keep an eye and I call you if there is anything there.
Okay. I think I'm going to do it in a different way because I have two screens, so I need to.
Oops, sorry, I sent a chat that was supposed to be private in the public chat. Just hugs. Everyone, please feel hugged. So you interrupted the sharing?
Yes. I'm changing screens here just to make it easier for me. I'm sharing it now, no?
Yeah, it's working again.
Okay, it's okay.
So I think we can start. It's already 2:10. So for those of you who are joining COLMEA for the first time, it's a joint seminar with 6 universities here from Rio, and it's not joint between universities, but also between departments. We have physics and statistics, mathematics together, and it's a pleasure to have Nuno Araújo from the Faculty of Science of the University of Lisbon here with us. He sent us a very intriguing title and abstract and description of the talk. I'm very much looking forward to see kinetics of self-folding at the micro scale, which he said will involve Kikigami and random walks, and very much looking forward to it. Please, Nuno.
Okay, so thank you very much. Good afternoon to everyone. Augusto, thank you for the invitation. It's for me a great pleasure to have the opportunity to discuss with you a problem that we have been working on over the last 2 or 3 years, and that is related to, as you said, to kirigami. So the idea is to obtain 3D shell-like structures, like, for example, this convex polyhedron here, the soccer ball, from the folding of a 2-dimensional template that consists of rigid panels connected through flexible hinges. And what I expect, or I aim at convincing you today, is that looking into this problem, especially when you do it at the micro scale, is related to random walks, graph theory, and other types of classical problems that you are familiarized with. So this is something that we started here at the University of Lisbon in collaboration with Cristóvão Dias and Igor Melo, that are researchers here in the group, but also in collaboration with people from another university in Portugal, that is the University of Aveiro, Rui Costa, Dorogovtsev, and José Fernando Mendes. And yeah, so what is kirigami? Let's start with origami, that everyone knows. So in origami, the idea is that you start with a sheet of paper, 2D sheet of paper, and you fold it in such a way that you get a 3-dimensional structure. So if now, besides being able to fold, you are also able to cut the sheet of paper, then this is what is the Japanese art of kirigami. And I'm pretty sure that all of you have played with something like this in school. So you start with a T-shaped template and you fold it in order to obtain a cube. So this is something that has been studied from many different perspectives. But what we have been looking at is how to do that at the micro scale. So the idea is that when you look into the micro scale, so when the size of the panels is of the order of a micron, then thermal fluctuations are important. So you expect that the faces will be moving around in a random way due to thermal fluctuations. And so you can imagine that if you have these rigid panels connected through flexible hinges that experimentally can be, for example, using solder at a temperature that is melted, so is in liquid form, then, and if you have sticky edges along these solid panels, so you might expect that by moving around, when 2 faces come together, they will close an edge between them. And if you do this process iteratively, so you can expect that you will get the final 3D shape spontaneously from the random motion of the different faces. And so what we have been trying to do is to try to come up with a theoretical framework that will allow us to describe this type of problems. Obviously, folding is something that has been studied by the physics community from different perspectives. And what we know is that the folding mechanism strongly depend on the length scale that we are looking at. So if you think about folding at the macro scale, that the centimeter scale, it typically occurs through some stress relaxation, and therefore not only the folding path, but also the final folded configuration is unique. By contrast, if you look to the nanometer scale, like for example in protein folding, then the interaction between the different components of the protein, the different amino acids, becomes important. And therefore, although it's believed that the final folded configuration corresponds to a minimum of the free energy, the folding path depends on this interaction between the different components of the protein. In between, at the micrometer scale, the one that we are interested, the interaction between the different elements that here are the faces of, will later become the faces of the polyhedron that we are looking at, is mainly an excluded volume interaction, so they cannot overlap. And the folding process occurs through a sequence of these binding events between the different faces, and therefore is a kinetic process. The final folded configuration will depend on the sequence of edges that are closed. From the experimental point of view, the challenges are mainly related to defining where the material will fold. And there are possible techniques to do that, in particular by using materials with different properties or that react differently to external stimuli, like for example, light or heat. But what I would like to focus is on different theoretical challenges that are related to this self-folding at the micro scale. So the first thing is, given a certain shape, and for simplicity, as I said, I will only consider convex polyhedron here. The first question that you can ask is, what is the net that can be folded into the targeted structure that we aim at? And so one way to do that is to do a process that is named as edge unfolding. So the idea is that you start with the polyhedron and you cut along the edges and you try to find a cut for which you end up having an open structure that is a two-dimensional structure. And this is what we call the net. So the net is the union between the faces of the polyhedron that is in a two-dimensional configuration, and the cuts cannot be done arbitrarily. They need to fulfill a certain number of conditions. In particular, we want that the net is a simply connected piece. The second thing is that should be the union of the polyhedron faces, so we can only cut along the edges, you cannot cut through the faces, and that this net should not self-overlap, is a really two-dimensional structure in that sense. And so the question is, does every convex polyhedron have a net? We believe that the answer to this question is yes, but as far as I know, there is no formal proof that for every convex polyhedron, there is a net. What people know is that up to now, nobody succeeded finding a convex polyhedron for which there is no net. But this is still an open question in the field. Okay, but as I said to you, we want that the structure folds due to the random motion of the faces. So you need to guarantee that somehow when two faces meet, that they are the ones, they correspond to what we call native binding. So it corresponds to two faces that are supposed to be connected in the final folded configuration. However, even in the case of the cube, there are 11 isomorphic nets that can fold into the cube. And therefore, the one interesting question is, what is the one that will be optimal in terms of self-folding? So we are really looking to a problem of n to 1, where n is the number of nets and 1 is the final folded configuration. So I think we have a question there, right? Yanis, you raised your hand, I think.
Yes, I wanted to ask about the proof to the question you said earlier, whether every polyhedron has a net. Is that like so far? Is that how do you find the net? Is that a constructive proof? Because if it's a constructive proof for any polyhedron, you can see, you can check if it has without caring if generally every polyhedron does. Is that something that's
no? Okay, so for a given polyhedron, we know that there is a net, right?
okay?
What you have no formal proof that for every polyhedron there is a net. Okay.
But why would we care if there is such a theorem? If
Okay, because if there is known, it means that there is a subset of shapes for which you cannot apply the ideas that we are talking here, right? So thinking more in general terms, think about any three-dimensional shape. In principle, and this is something that people working, for example, in computer vision, they do that, you can discretize the surface into, through triangulation, for example, into triangular shapes. So if you can show that for any convex shape, you have such a net, then in principle, this is so general that you can have any structure being obtained from the folding process. But for the sake of what I'm going to say today, I will focus on polyhedra for which I know that there is a net. But I cannot make it a general statement saying that this is valid for any shape.
I see. But in any case, even if you proved it, you will still need to construct it. So proving it doesn't save you, right?
Exactly. No.
That's my point. Okay.
I will be talking about that. So one thing is to prove that there is a net. Another thing is how to identify the net. And in particular, as I'm showing in this slide, how to identify which one is the best one, right? And this will be the subject of the first part of my talk.
Okay, thank you.
Bear with me. Okay. So as I was saying, so even in the case of the cube, you have 11 non-isomorphic polyhedron, 11 non-isomorphic nets. And so you can ask, what is the optimal one for self-folding? What is the one that will maximize the probability that the final folded configuration is the cube, or for any polyhedron, what is the one that maximizes the chance that you get the targeted three-dimensional shape? Well, the problem is even more complex than that, because imagine that you take this net. So if you now connect the faces based along the edges, based on the letters that I have here. So if you connect A with A, B with B, C with C, D with D, and E with E, then what you get is the boat-like shape. But if you start now from the same net, and you recall that what we have is a random motion of the faces. If now they connect with a different sequence, in particular, if these two now connect with each other, B with B, C with C, D with D, and E with E, you get a different shape. So this means that not only the net, the same net can end up being folded into different configurations depending on the sequence of the edges that are binded to each other. And so what has been shown both from with simulations and through experiments, the experiments were run at Johns Hopkins University in the US, and the simulations, the first numerical simulations are by the group of Sharon Glotzer at the University of Michigan, is that the final folded configuration depends not only on the initial template, but also on the kinetics of folding
In other words, it depends from, if you take two different samples, they might end up in different configurations. And so what are the kinetic pathways of folding? What are the structures that are formed? How they depend on the initial configuration. And so we are really looking to a problem of N to M, where N is the number of possible templates and M is the number of possible folded configurations. And we don't even know for each template how many possible final states exist. So to address this problem, one of the things that has been done from the experimental point of view is to set up a system and ask if there is some geometrical property or topological property of the net that can indicate, that is a good proxy to identify if the net is optimal or not, or is good or compared to nets in terms of wilding, in terms of percentage of samples that will fold into the desired configuration. So let me describe you a bit the experiments. The way they do it is that they synthesize the faces using some metallic material, and they connect the faces to form the net, as for example, the example that I'm showing you here, using solder. But the way they do it is that they have solder not only to the faces that are supposed to be connected, but also along the edges of the other faces. This is initially synthesized on a substrate, but then they heat up the system. And so when they heat up the system, the solder will melt, and therefore the faces that are in contact, these hinges will become flexible. And as I said, due to thermal fluctuations and the motion of the fluid where these structures are in, then the faces start to move at random. And when two faces come together, like for example, when these two edges come together, then they will stick to each other because you still have molten solder there. So they become sticky. And so what they did is that they performed simulations starting from different nets, and they followed the folding process. And in particular, they decided to compare a topological and a geometrical compactness to check which one will be the best criterion to define what is the optimal net for self-folding. So geometrical compactness is only to look at the radius of gyration. So they synthesize different nets, and they put this hypothesis that the best one for folding, the one that will be more efficient in the folding process, is the one with the lowest radius of gyration. And they put this criterion against the second criterion, that is a more topological one, that is saying the best net will be the one that maximizes the number of vertex connections. What is a vertex connection? A vertex connection is a vertex that has only one edge that has been cut in order to open the structure. The idea is that during the folding process, for each vertex connection, you have one vertex connection here, another one here, and another one there. There are several vertex connections in this structure. If you maximize the number of vertex connections, you maximize the number of vertices where you only need to close one edge in order to fully close the structure around that vertex. And so they decided to compare these two different criteria. And the way they do it is that for each three-dimensional shape, they take 6 different nets. 3 of them correspond to the lowest, the highest, and the intermediate value of the radius of gyration, and the other 3 to the maximum, the minimum, and the intermediate value of the number of vertex connections. And so for each one of them, they run 50 independent samples experimentally, and they classify the final folded configuration into 3 different groups. If the final folded configuration corresponds to the targeted structure, then they classify as A, corresponding to a defect-free folded configuration. If instead they differ by less than, I think it's 5 degrees in the angles between the faces, then they call a minor defect. While if it is different from that, then they say that is a defective configuration. And so what you are seeing in this plot is for each of the nets, in the left case for the dodecahedra, and in the right hand side, the truncated octahedra, they plot what is the fraction of configurations that end up in being A, B, and C. And the first three nets are ranked by increasing value of the number of vertex connections, while the other three are by decreasing value of the radius of gyration. So you can clearly see that both criteria lead to an increase in the fraction of configurations that are defect-free. So it's a good criteria to identify nets that will fold in a more efficient way. But you see that the number of vertex connections is more efficient in terms of criterion than looking into the radius of gyration. The problem is that in order to identify the configuration that maximizes the number of vertex connections, what people have been doing is basically to generate all possible nets, and from all those nets, for each one of those nets, to count the number of vertex connections and look for the configuration that maximizes the number of vertex connections. And so, as you can imagine, as you increase the number of faces on the polyhedron, this becomes a very difficult task and very time-consuming and computational demanding task. So what we did in 2018 was to show that, in fact, instead of doing the strategy of mapping all the cases, or for large polyhedron to do it at random and try to find a configuration that maximizes the number of vertex connections, you can do it in a deterministic way by mapping the problem into a graph. So the way it works is very simple. You can define a graph here that is what we call the shell graph. So the shell graph is a graph where the nodes are the vertices of the polyhedron, and the links are between vertices that share an edge. And so here is represented in black. So the nodes are the vertices and the edges are the links, or the links are the edges of the polyhedron. You can also define the face graph, that is a graph where the nodes are the faces, and you connect nodes that share at least one edge. So by doing this edge unfolding process that I described to you before, what we'll be doing is by cutting this shell graph along some of these links in order to open the structure. So we can define the cut graph, that is a subgraph of the shell graph that corresponds to the edges that you need to cut in order to open the structure and obtain the net. So this is what I'm doing here. I'm taking the cube, I'm cutting the cube according to these red lines that I'm showing you here in the cut graph, and obtaining the open structure that will be the net that can fold into the cube. Okay. And as I said before, there are a certain number of constraints in this edge unfolding process, and you can extend those constraints here to the cut graph. So the first thing is that the cut graph needs to span all the vertices. So if you assume that all vertices have a non-zero curvature, then it means that you need at least to have one cut that arrives to this vertex in order to open the structure and guarantee that at the end you have a zero curvature around that vertex. The second thing is that it should be loopless, because if you close a loop in the cut graph, then you remove a face, and you want to open the structure without removing the faces. Remember that at the end, the net should consist of the union of all the faces. So if you close a loop, you remove a face. The third thing is that it should be a simply connected structure in order to guarantee that you open the structure to the same side and you really get a two-dimensional structure. Because if it is not a simply connected graph, what you will have is that half of the structure opens in one direction and the other will open in the different direction. And therefore, it's not guaranteed that you'll have two-dimensional structure at the end. So what you need is to start from the shell graph and look to the subset, that is the cut graph, that fulfills these three different criteria: spans all the vertices, is loopless, and is simply connected. And this is what we call in graph theory the spanning tree. So what you need to identify is what is the spanning tree of the shell graph. So the set of all possible nets corresponds to the set of all spanning trees of a shell graph. But remember, what we want to identify is the optimal one. And the optimal one is the one that maximizes the number of vertex connections, the number of nodes for which you only have one cut. And so in the language of graph theory, it means that the cut graph, the ideal cut graph, is the one that maximizes the leaves, the nodes that only have one link, because it corresponds to the vertices that will have only one cut. So looking for the optimal net corresponds to looking to the maximum leaf spanning tree of a shell graph. And this is something that there are many algorithms that can help us doing that. And so therefore we can do it in a deterministic way and finding a unique solution for our problem. In fact, it's not a unique solution, but you can find a deterministic solution to your problem. You can find all the maximum leaf spanning trees. And one interesting thing is that when you compute what is the number of maximum leaf spanning trees, the number of optimal nets, the fraction of spanning trees that are maximum leaf spanning trees, so the fraction of nets that are optimal, you clearly see here in a log linear plot that it decays exponentially with the number of edges in the polyhedron. And what you are seeing here is the values, the numerical values for all the Platonic solids, for all Archimedean solids, and a bunch of other solids that we have looked at. And you clearly see that you have an exponential decay, meaning that the probability that you would find those optimal configurations using random methods, it's decreasing exponentially with the size of the polyhedron. And therefore, you really need deterministic methods like the ones we are proposing. So just to have an idea, if you take the dodecahedron, it has of the order of 2,000 maximum leaf spanning trees out of 5 million spanning trees. It means that if you just look for them at random by generating a net, counting the number of vertex, you will find one optimal out of each 2,500 samples. So therefore, your success rate is of the order of 0.04%. So you completely can forget random methods, and you really need to find a deterministic way like the one we are proposing here. In fact, we can explain this exponential decay by setting an upper bound for these quantities. In particular, if you think what is the number of spanning trees, you know that a spanning tree is a loopless structure that has as many nodes as the number of vertices in the system. And the way, so it means that it has v-1 edges, where v is the number of vertices in the system. So the maximum number of spanning trees is a combination of edges, of all the edges you have, where you take v-1. So this is an upper bound for the number of spanning trees. And you can do the same for the maximum leaf spanning tree. So the ones that maximize the number of leaves is, if you know what is the maximum number of leaves you can have, then the maximum number of maximum leaf spanning trees is the combinations of VL. So by looking to our numerical data, we can see that the number of leaves scales with the number of linear with the number of edges. The number of vertices scales with the linear with the number of edges according to this law, and therefore you can explain why you have an exponential decay by relating these two different quantities. Another advantage of our method is that you really get a catalog of all maximum leaf spanning trees. In principle, you can get a catalog of all maximum leaf spanning trees, and therefore a catalog of all optimal nets. And so you can apply a second criterion on top of that. And what we are showing here, just as an example, is that you can look, for example, to the radius of gyration. So you first choose the nets that maximize the number of maximum leaf spanning trees, the maximum number of vertex connections. And from all the nets that have the same number of vertex connections, you can choose the ones that have the lowest radius of gyration. And the combination of these two methods is quite successful. You can see that only in less than 20% of the cases is when you don't find a structure that resembles the targeted structure that you aim at. And here is just an example for the soccer ball, where you can see that you have 4 of the order 4,000 non-isomorphic structures. And in that case, if you plot now the ratio between the radius of gyration and the minimum value that you can get, the optimal case, you clearly see that even when you take the 4,000 different maximum leaf spanning trees, and you rank them based on the radius of gyration, is that even if the number of vertex connections is the same, you still see that the radius of gyration strongly depends on the net that we are looking at. And by having this full catalog, we can really go and find which one is the optimal out of all these possible structures. Okay, so this is related to how to identify the one that maximizes the chance that you get the final structure. But when you think about optimization of folding, you can think in two different ways. Optimizing in terms of maximizing the chance that you get the targeted structure without defects. And this is what we have been discussing so far. But you can also think in terms of minimizing the folding time. And so what we decided to look at is how does the time for folding depends on the initial configuration. And so the first approach was to do some direct numerical simulations of the motion of the different faces. So the way we do it is that we take a net and we represent it in the computer by using a discrete number of particles. So we have a particle per vertex of the face and another particle at the center of the face. So the ones on the vertex are here represented in blue, the ones at the center of the face are represented in red. And we follow the dynamics by considering that we have a repulsive interaction between the, we have a repulsive interaction between the ones on the faces, on the center of the faces, the red ones. That is just a simple exponential decay of the repulsive interaction that will represent this short range repulsion of the faces, meaning that they cannot overlap, that will correspond to an excluded volume interaction, and that we have an attractive short range attractive interaction between between the blue dots, meaning that we have sticky edges between the faces. And this will guarantee that when two faces come together, they will stick together in an irreversible way, meaning that within the time scale of the simulations, these bonds will not be broken. So they will remain together for the remaining of the simulation. And with that, you can really follow the folding process, as you can see in these two videos that I'm showing you here. So what we did is we take the case of the cube. As I said, we have 11 non-isomorphic nets that can fold into the cube. And we look to the percentage of wilt, as we did before. And here, so what we have is in the horizontal axis, the rank in terms of percentage of field, in terms of percentage of samples that have folded into the proper final folded configuration, for the 11 different nets. And in the vertical axis, what we have is the maximum number of vertex connections. And you clearly can see that there is a positive correlation. If you maximize the number of vertex connections, you also maximize, again, this is the rank when you go from the highest to the lowest number of maximum vertex connections. And therefore, if you maximize the number of vertex connections, you also maximize the wilt. These numbers are in terms of position in the rank. The same for the minimum radius of gyration. You also see a positive correlation between the two. So the two are good criterion for the percentage of wilt. However, if you now, and this will be the three best configurations in terms of percentage of configurations that fold into the proper final configuration. However, if you look in terms of folding time, you see that the top three is significantly different. In particular, the one that is the fastest folding is this configuration here, that is not in the top three in terms of percentage of wilt, in terms of fraction of samples that fold into the desired configuration. So you really see that looking to optimization in terms of time is significantly different from looking to optimization in terms of percentage of successful cases of folding. And it's not yet clear what will be the topological, geometrical criteria that will tell us what are the best ones to fold in terms of folding time. So since we could not come up with an explanation for that, we decided to do one step back and go to a simpler problem. So we take the case of a pyramid. So we have a pyramid with n faces, all faces are equal. And so we raise the following question. If you fix the pyramid to a basin, to a substrate, and you only let the pyramid to fold into one direction, the question is, how does the folding time depends on the number of faces? And what we see is that we get a non-monotonic dependence of the folding time with the number of faces. We clearly see that the folding time initially decreases with the number of faces. So it becomes faster if we increase the number of faces, but if you keep increasing the number of faces, it increases again. And you see that you have an optimal value of the number of faces around 5. So this was a result that initially we got from the numerical simulations, and we tried to understand what was going on. So the way to analyze this problem was first to define what is the proper degree of freedom to look at. And we decided to look into the angle that each face makes with the substrate. So remember, we have a substrate, we have the pyramid, the base of the pyramid sticks to the substrate, and the faces can move, but they can only move along towards one of the directions. And this guarantees that you have no misfolding. And the other thing that we are assuming is that they have sticky edge, but they also have a sticky vertex on top. So if two faces meet on top, they will close. And so what the first thing we did was to plot the value of the angle of the faces here for a simple case of a pyramid with 3 faces as a function of time. And the first thing we see is that the statistics of the angle, this is obtained by molecular dynamic simulations like the ones I described to you before. But the first thing we realize is that the statistics of the angles is consistent with a random walk. So what we have is that each face is doing a random walk in the space of the angles with a certain diffusion coefficient that depends on the properties of the faces. But it's a random walk and is confined because the angle is can only take values between 0, that corresponds to have an open structure, and pi, that corresponds to have the faces close to the opposite direction. When you look to the time series of these angles, here 3 different colors corresponding to the face A, B, and C, what you see is that you get this random motion, and you have 2 closing events. A first closing event occurs when the 2 faces meet, the first 2 faces meet at the closing angle, that here is represented by this blue horizontal line here, corresponds to the angle at which the 2 faces will close. And so first what we have is this first closing event where the 2 faces meet, and then you have a second closing event that corresponds to a third face coming and meeting these 2. And so clearly, the folding process can be seen as a sequence of binding events, but they have 2 different natures. The first binding event corresponds to the closing of an edge between 2 different faces, while the second and remaining closing events for a pyramid of n faces corresponds to an individual face to meet the other two that are already there at a specific angle. And as you can already imagine, what we are thinking about is first passage processes. So let's look to these two different processes separately. So the first closing event, as I said, corresponds to the case where you have two faces that meet at a specific angle that is the closing angle. A way to look to that is to look into a two-dimensional problem where each coordinate, the horizontal and the vertical one, corresponds to the values of the angles. So in the horizontal angle, for example, if I think about two faces, on the horizontal axis, I'm representing the value of the angle of one face, and in the vertical axis, the value of the angle of the other face. And so what I'm looking, since they are uncorrelated, is to a 2D random walk. So the motion of these two faces can be seen as a 2D random walk, and they will close when the two of them meet at a specific angle. So it means the first time that they hit a region in this two-dimensional space that corresponds to this region here. So what we are looking is to a 2D first passage process. But in fact, since we have n faces, the question that we are asking is, what is the fastest of all possible 2D first passage process that we have in the system? And so if you calculate what is the typical time for this first closing event, obviously, if you assume that you have n large, what you will see is that it needs to scale as something like 1 over the logarithmic of the number of pairs. So n times n minus 1 over 2, where n is the number of faces that we have in the pyramid. And once these two faces close, all the remaining faces, they just need to meet these two faces. So they just need to hit this specific angle for the first time. So what you can see here is that what we have is for all the other faces is a 1D first passage process. And so the time it takes from the first closing event until you totally close or totally fold, the total folding time, it's the slowest of all the other n minus 2 1D first passage processes. And so if you think in terms of rank statistics, you want to ask from n minus 2 first passage processes, what is the typical time of the slowest of them? And you know that needs to scale as the logarithm of n minus 2, where n minus 2 is the number of first passage process that you want to have. So if you now combine the two, what I'm showing you here is that the folding time as a function of the number of faces. So you see that the total folding time is the first folding time plus the time it takes from the first folding time to the last face to close. And so the purple dashed line is how the first folding time should scale with the number of faces, while the green dashed line is how the last folding time should scale with the number of faces. And so this logarithm of n minus 2, when you add the two, what you get is this solid blue line. And what you are seeing here with the dots is the values that you obtain from numerical simulations by considering different number of faces, different closing angles. And so you clearly see that what you get is a folding time that follows this line, and therefore you get the data collapse, and therefore it shows that the minimum occurs because you have a balance between the time it takes for the first two to meet, and this is something that should decay with the number of faces, and the time it takes for the last one to close, and this is something that should increase with the number of faces. So it implies that for low values of the number of faces, what dominates the time scale is the first closing event, while for large values of the number of faces, what dominates is this time that you need to wait for the last one to close. And so with that, we can explain the minimum. Obviously, what we have here is an approximation, is far from being an exact result. And my last slide is related to that. I want to give you some food for thought. That is how to be able to derive an expression for how does the first closing event depends on the number of faces. And so one of the things we have, and sorry, and so this is the first thing. And the second thing, the second problem that you can think about is how to compute the total folding time. Even for the case of three phases, we have not yet come up with a closed form equation for the total folding time. And one of the problems we have is related to this. Imagine that you start with three phases. So what we have is three random walks, and you can in principle calculate what is the time it takes for the first two to close. But once you have that, what you need is to compute what is the time it takes for the third one to meet these first two. And as I said, this is a 1D first passage process. However, you need to start with some initial condition. So even this question of where is the third particle when the first two meet is already an interesting one. Because as you can see here, what I'm showing you here is the probability that the third particle is at a certain angle theta as a function of theta. And this is obtained from numerical simulations. So you clearly see that you have a depletion in the closing angle, that in this case was 120 degrees. So, but you see something that is asymmetric. You don't have a uniform distribution, but you need to know this distribution in order to compute what is the typical time for the first passage process that will tell you what is the typical time for the third phase to close. And what you can see here is that if you do the approximation of saying that it is a uniform distribution of the third angle when the first two meet, we will be underestimating the last folding time. So somehow the last folding time is higher than the one that you would predict by assuming that you have a uniform distribution. So this is something that we don't know yet, for example, how to calculate. And this is just one example of several open questions that we have related to this problem. So, okay, just to summarize, the main points of my talk are that first, folding is a really interesting N-to-M problem, where N is the number of nets and M is the total number of folded configurations. That finding the net that is optimal in terms of folding efficiency is equivalent to maximize the number of single vertex connections, and this corresponds to the maximum leaf spanning trees of the shell graph. That this method provides a unique and optimal solution, that together with that you get a full catalog of all the nets that fulfill the criterion of the maximum number of single vertex connections, and therefore you can think about applying other additional criteria, and that looking to optimization in terms of folding efficiency is not necessarily the same, is in fact very different from looking to folding time, and that the folding time is a non-monotonic, even for the simplest case of a pyramid, is a non-monotonic function of the number of faces, and that we can explain this non-monotonic dependence by looking to the problem as a first passage process, as a set of first passage processes in 2D and 1D. And I did not even discuss what we know for more complex structures where we have a hierarchy of folding. So as you can imagine, as you make the structure more complex, the things become even more difficult to tackle. So thank you very much for your time, and I will be happy to answer any question you might have related to this topic.
So thank you, Nuno. So I read the questions in the chat when they were already not, the subject had already moved on. So Yanni has several questions. First, you can read them on the chat, but I have mine as well after you go through them.
Maybe Yannis can explain his question. Maybe it's easier, no? I don't know.
Yes. No problem, but since I already asked one question during the lecture, if somebody else wants to ask, we can go to I can defer my questions later. I mean, it's fine.
I think you are the one with more questions. So.
Okay.
Go ahead.
Okay. Now let's go backwards. Now in your slide where you have the simulation as a number with a number of phases, I noticed that you went up to 30 phases, and I'm asking why can't you go at least one order of magnitude bigger, like 200? I think would be interesting to see how.
I'm sorry. You say here.
Yes. Yes.
Okay.
And then the corollary to that is that connected to the computational complexity? And can you talk a little bit about the computational complexity of the simulations?
Yes. Okay.
Thank you.
So in fact, we have 3 ways to do this problem, right? So one of the things we did was direct numerical simulations of the phases using MD, as I showed to you before, where we discretize the phase into different vertices and we follow the dynamics. So we really resolve the trajectories of the different phases, and we compute the interaction between the phases, possible excluded volume interaction between the phases, the fact that when 2 phases come together, you have some repulsive interaction and things like that. So this is something where the complexity of the numerical simulations increase drastically with the number of phases, right? Because the number of interactions you are considering increases with when n squared, and where n is the number of vertices now, or if you will, is a linear function of the number of phases. So that's why, since here we were comparing with those simulations, then we were limited in the number of phases. But there are 2 other ways of looking to this problem. One is to solve the equations of motion using the Langevin approach. So you have a stochastic differential equation for the value of the angle, or you discretize the problem and you solve it on a lattice. We did both things. What is the problem there? There, what we have been doing so far is to neglect any excluded volume interaction between the phases. So what we have is random motion of the phases, and they are completely transparent except if they meet at the closing angle. So in those simulations, you can really take them to the limit. You can do 2 orders, 3 orders of magnitude without any problem, larger. We can do up to, I don't know, 100,000 phases will not be a problem to be considered here, because it's just a problem of random walks, right? What we have seen is that at least in the regime between 0 and 30 phases, these interaction that we are neglecting, this excluded volume interaction between the phases that we are neglecting, does not affect the final result. And that's why we stick to this limit, because we always had in mind these systems of the physical system where you do have this interaction between the phases. And we are thinking about more complex structures where these phases, if you think about the cube, then the interaction between the phases really plays a role. So this is the reason why we were limited to 30. But if you think in just random walks, you can really take this to the limit. And I don't think you will have a different behavior. I know what you have in mind is basically to really validate this logarithmic scale in n-2, right? And I don't think we'll have a serious problem there. It's something that we are really seeing it for very large number of phases. I think that I have more concerns about the initial dependence that is 1 over the logarithm of the number of pairs. This is where I have, I would like to see a more exact result, if you mean. Was it clear?
Thank you. Thank you. Yes.
Other question? I think you have more questions, right?
Yes. Back in the graph where you were showing the folding time as versus the number of phases, I had a question. If I mean it increased. Remember, it was non-monotonic.
This case you mean? Yeah.
The slide I was referring was a little bit earlier.
This one.
Yes, and I'm thinking whether it's plateauing. As again, it's similar to the previous question. If you increase the numbers of phases, it looks to me the graph is kind of like cusping, like it's plateauing.
It's because it's the logarithm of n.
Okay.
It's just a consequence of being logarithm of n, or n minus 2, if you will. And so basically, it's the shape that you are seeing is the shape of a logarithm of n minus 2.
Okay. Okay. All right.
So I have a few questions. One, first of them is quite naive. It's about the synthesis process of this. You gave the impression that it's something similar somehow to how you produce silicon substrates for processors. Is there?
Well, it's slightly different, but it's similar in the sense that you also do it in a substrate, but you are not doing the position here, right? So the sizes here are not atomic scales. So it's micrometer scale. So you can also take a sheet of material.
Early computers, right?
Huh? Yes.
Early computers are also.
Yes, the first transistors. No, but basically what you can do is to start with a sheet of metallic material, using a laser to cut it, and then you solve the ones that you want to have, and then you wash out and you remove the others. You know what I mean?
And are these gonna be a robot soon?
That's the point. My point here is, you think, for example, about robotics, and people have been thinking about robots that are shape-changing materials, that they change their shape depending on the environment or the function that they need to make at a certain time. When you go down to the micro scale, you obviously can extend some of the ideas that you have at the meso macro scale, but you need to account for thermal fluctuations. And you see, if you look to different experiments that the people have been doing with robots at the micro scale, if you talk to them, they will tell you, well, the problem here is that thermal fluctuations make that these things are shaking. And what we are saying is that if you choose the structure in a smart way, you can take advantage of those thermal fluctuations in order to obtain the closest structure. And one of the things we have done, I did not show here, is that if you have a drive, because typically you have a drive, you have some kind of actuator that is forcing them to close, you still see this non-monotonic behavior. Obviously, the minimum will no longer be in 5, it shifts a bit, but you still see the non-monotonic behavior. So understanding the thermal fluctuations, even in the case where you have no drive, could give you some insight of what will happen in the case of a robot. Yes.
A second question I have is, if you've studied the pyramids and you had some heuristics that go around that base phase to estimate the time to fold on that particular place. Yeah. Do you have hope to use that local understanding that you now have to go back to a nice larger net and try to come up with some heuristics about the total time?
Yes, that's an interesting question. So take the example of a cube, for example, right? A cube, if you think about the T-shaped net that I showed in the beginning, the closing, you'll have 4, more or less, you will, as a first approximation case, consider you have 4 equivalent faces that need to close, and then you have the tip that needs to close afterwards, right? Yeah. I see this as a hierarchical process where you have a first closing event of the first generation of edges, and then a second one. If I know how the closing time for each one of these generations depends on the number of faces and local structure, as you say, then I could build a recursive method that will tell me what is the final closing time, because you know that you have this hierarchy of closing where the first ones need to close in order for the second one to close. So we have been exploring ideas like that, that if you could have like a catalog of possible closing events, and with that try to predict what is the final one. This is something that we have in mind.
And just one last comment, sorry, it's not a question, but the last slide, you really reminded me of quasi-stationary distributions. That it's something we see a little bit in the mathematics community, but maybe not so much. Maybe it's not so famous for physicists. So it really gives you the, instead of the flat uniform distribution, gives you a good way to think about the time to collapse. So we can talk about this later. But
Okay. Quasi-stationary distributions. Okay. I will look at that. Good.
So are there any more questions? Okay, if no, let's thank both Marcelo and Nuno again for this wonderful.
Thank you very much.
colloquium.
Thank you for the opportunity.
Thank you very much.
And we'll continue, as I said, with the seminar next Wednesday and with COLMEA on March, if I'm not mistaken.
Next COLMEA will be on April 13th, and it will be about environment. So we'll have Paulo Artacho and Mariana Del Valle about climate changes and about the impact of climate change on pandemics. So it will be a completely different subject.
Very nice. Okay, thanks everyone.
Tudo bem?
Oi.
Oi, Hilário.
Oi, Leandro. Tudo bem? Muito obrigada, Nuno. Obrigada, Marcelo.
Obrigado eu. Olá, Marcelo.
Obrigado aí, Nuno.
Olá, Marcelo. Olá,
Obrigado,
Nuno. Fez a apresentação, tá bem?
Obrigada. Se você me manda por e-mail, pode ser.
Pode mandar para mim.
Porque por aqui eu fico, ou para o Augusto, tanto faz. Por aqui eu tenho, fica meio ruim de pegar, sei lá, não estou acostumado.
Ok, ótimo. Tá bom.
A gente acabou te segurando até um pouco tarde aí no gabinete, né?
Hã?
A gente acabou te prendendo um pouco até mais tarde.
Não, ainda são
hoje.
6 horas, ainda tá dia lá fora.
Vantagens do verão.
Exato. Ainda estamos muito longe do verão, ainda é inverno, assim.
Está no verão? Não, está no...
Inverno,
tá no inverno.
ainda.
Então isso Então, Lisboa é um luxo. Se no inverno, 6 horas você ainda tem sol.
Não, de Lisboa, também por causa da proximidade o sol também, claro. E dada a proximidade ao mar e ao rio, a temperatura também não vai muito fria, nem vai muito quente. Mas para o sol também é bom. Nesta altura, fica a noite agora às 7.
Também vocês têm o mesmo horário de Bruxelas e estão bem a oeste, né? Então o sol se
Não, nós temos menos 1 hora.
Menos 1 hora? Então não tem essa vantagem. Então tá muito
horário
bom.
de Londres.
Inverno, 6 horas, eu lembro. Inverno, 6 horas, já estava bastante escuro em Zurique.
Mas nós estamos mais a sul, não é? Essa sorte. Não pode ser tudo mau, não é?
Não estou vendo nada mal, na verdade.
É bom. Boa.
Tá bom.
Bom.
Estou indo, então.
Eu também.
Gente, obrigado. Então,
obrigado por tudo. Augusto,
obrigada. Pessoal,
Marcelo,
tchau.
bom ver-te.
Tchau.
Muito bom te ver, Nuno.
Interrompeu lá no YouTube, né?
Como?
Interrompeu lá no YouTube, né?
Acho que ainda não.
Parece que ainda não. É porque
aqui
tem
eu ainda
que
estou vendo.
interromper.